Objectives. Understand the importance of linear programming and what is it all about. Learn how to execute the steps in solving linear programming problems using the graphical method. Apply linear programming in real-world scenarios and its practical implications.
To our esteemed instructor, fellow classmates, and our valued listeners and viewers, good day. Today, we are delighted to present to you a topic that delves into linear programming using the graphical method. To provide you with some insights about our topic, let me begin by giving a brief definition of what linear programming is all about and how it holds importance in our daily lives. Linear programming is a mathematical modeling technique that aims to maximize or minimize a linear function while considering various constraints. Its significance lies in its ability to enhance the quality of decision making by calculating the cost and profits associated with different variables. This makes it particularly relevant to our field as tourism management students, where we frequently analyze aspects such as cost and profit. Are you ready to embark on a journey of learning something new today? I encourage you to watch this video until the end and make sure to take down notes. Thank you and enjoy our presentation.
Linear programming is a mathematical method used to optimize a linear objective function while considering linear constraints. Let's break down some key terms related to linear programming. Objective function. This is the function that we aim to maximize or minimize. It represents the goal we want to achieve, such as minimizing profit or minimizing costs. Decision variables. These are the unknown quantities or variables in a linear programming problem, typically represented by symbols like x, y, or z. We adjust these variables to find the optimal solution. Constraints are the condition or limitation that restricts the feasible solutions in a linear programming problem. These constraints can be resource limitations, production capacities, or other restrictions that need to be considered. The feasible region is the area on the graph that satisfies all the constraints. It represents the set of solutions that meet all the given constraints. The optimal solution is the solution that maximizes or minimizes the objective function within the feasible region. It represents the best outcome based on the given constraints and objective. A corner point is the point on the graph where two or more constraints intersect. These points are important because the optimal solution often lies at one of these corner points. As a profit line represent the different levels of profit in a linear programming problem. It helps visualize the trade-offs between different levels of profit or cost. Shadow price, also known as dual price, measures the change in the objective function value per unit increase in the right-hand side of a constraint. It indicates the marginal value or relaxing or tightening a constraint.
So here are the problem. Fly High Airline sells business class and tourist class seats for its charter flights. To charter a plane, at least 5 business class tickets must be sold and at least 9 tourist class tickets must be sold. The plane does not hold more than 30 passengers. Fly High makes 40 centavos profit for each business class ticket sold and 45 centavos profit for each tourist class ticket sold. In order for Fly High Airlines to maximize profits, how many tourist class seats should they sell? So for the solution and the step by step will be discussed by Miss Claros and Miss Jenna.
So in this problem, we will have to find how many tourist classes should they sell for the fly-high airlines to maximize their profits? And in order to do that, we must first identify the decision variables that we will be using. So the X will represent the business class ticket sold, while Y represents the tourist class ticket sold. So after that, we will have to formulate the problem for the LPP model, which is the objective function and the constraints. So our objective function is a function where what is asked in the problem, and in the problem we have to maximize the profit. Therefore, our objective function is a P, which represents the profit, equals 40x plus 45y, where 40 comes from the $40 profit for each business class ticket sold, while the 45 comes from the $45 profit for each tourist class ticket sold. Next is the constraints. Constraints are the conditions that limits the feasible solutions in the LPP. And in this problem, we have three constraints, where our first constraints is x is greater than or equal to 5. X again represents the business class tickets, while the 5 are the goal of the airline, with having at least 5 business class tickets must be sold. The second constraint will be y is greater than or equal to 9, where y represents the tourist class tickets, and 9 is the goal of the airline of having at least 9 tourist class tickets must be sold. And lastly is the total number of seats sold cannot exceed 30, and this represents inequalities of x plus y is less than or equal to 30. The next step is to plot the following inequalities in a Cartesian plane. But before we do that, we must consider these inequalities as a equation. Therefore, the x is greater than or equal to 5 will turn into x equals 5, while y is greater than or equal to 9 will convert into y equals 9. Then lastly, the x plus y is less than or equal to 30 will convert into x plus y equals 30. And this graph below will show what it look like. So for you to be able to plot the following constraints on a Cartesian plane is that you will have first to find the coordinates of the following y-intercepts and x-intercepts. So in the first constraint, we will find here the x equals 5, where its x-intercept will be 5 and 0, while there is no y-intercept. Then the second one, the y equals 9, will have the y-intercept of 0 and 9, while there is no x-intercept. Then lastly, this equation will have an x-intercept of 30 and 0, while its y-intercept is 0 and 30. So now that we were able to plot the following equations in a graph, we will now have to proceed the next step, which is to identify the feasible region. So the feasible region is the area of the graph that satisfies all constraints. So since in the problem our goal is to maximize the profits, therefore the feasible region will be within the first quadrant. So here we can see the graph where the shaded part is inside the first quadrant, and there we will be able to see these vertices of A, B, and C that we will be using as our optimum points in finding our optimal solution.
The intersection points of the lines representing these constraints determine the vertices of the feasible region. The profit function is maximized at one of these vertices. Now, let's find the coordinates of the vertices. First, at the intersection of x equals 5 and y equals 9 is 5 and 9. Second, at the intersection of x equals 5 and x plus y equals 30 is the coordinates 5 and 25. And third is at the intersection of y equals 9 and x plus y equals 30 is the coordinates 21 and 9. Now we evaluate the profit function of p equals 40x plus 45y at each of the vertices. So to choose the vertex with the maximum objective function value as the optimal solution, so we have to change x and y to its desired coordinates. So in column A, we have a total of 605 as its objective function. Column B, we have 1325 as its objective function. And column C, we have 1245 as its objective function. The maximum profit is obtained when selling 5 business class tickets and 25 business class tickets. Therefore, to maximize profits, Fly High Airlines should sell 25 tourist class seats.
In generalization, linear programming using graphical method is a crucial tool for efficient resource allocation and decision-making in real-life scenarios. For example, in manufacturing, it optimizes production schedules while considering constraints like limited raw materials and labor. Next example would be it helps investment firms allocate funds across different options considering risk and return objectives. The graphical method provides a clear illustration of the situation, enabling decision makers to understand and communicate optimal solutions in practical terms. Therefore, in conclusion, linear programming is a mathematical technique used for optimization, and the graphical method is a visual aid that simplifies the process by displaying the feasible region determined by the intersection of the constraints and the outline of the objective function. The optimal solution is found at the point where the objective function is maximized or decreased. This method is useful for practical decision making and mathematical analysis due to its graphical interpretation of the optimization process.